So welcome, and now today we would be doing one exercise which is on sparse autoencoders. And while in the last lecture I have explained you exactly where and how sparse autoencoders come to play. So while we are doing this particular exercise using the MNIST digits classification problem, you would be exposed on to how to incorporate sparsity within your code, and then how does this have a subsequent down role to play down. So you clearly remember when we were doing down our earlier lecture on sparse autoencoder. So there was a L1 norm which was introduced over there, or what was also called as a L1 penalty loss, and that's basically to find out the total number of zeros which are present down, and then just do some sort of a K divergence between the total number of zeros present and the total actual desired number of zeros to come down. So that was a extra loss which we were adding down as an extra amount of error to the whole system, and the whole objective was that till we come down to the point where we desired to have we actually have that many number of zeros within the weight matrices as we would desire to have over there, this error is still going to be a higher value and then it would come down. So technically, if I desire that 30% of my weights over there are completely zeros, and if it's not up to that level, then it has a higher error. And on the other side of it, say I desire that it is 30% of them are zeros, but then 80% of my weights turn up as zero. So that's mean that I have a system which is learning to be heavily redundant, but I don't want the system to be that redundant. So I can actually because of a positive error coming down because of that K divergence function over there, you would see this metric actually coming to a point where it would come down to that 30% point over there. So that's a typical example which we will be doing. However, given one thing in mind, that we have just looked into one kind of a cost function, one kind of a loss function, and not these two kinds of different loss functions. So how to incorporate that within your network and whether that has any changes in the forward pass and in the backward pass is what we will be doing today. Okay. So starting from the first part, which is quite simple, and just on loading down your libraries and then eventually coming down to your loading down the data. So we are using the same architecture and same kind of a notion as in any of our earlier experiments with MNIST. So you have 60,000 training samples and 10,000 testing samples, and what we are doing is we call up the data set from our Torch Vision data sets point, and the advantage which we get down is that I have already downloaded everything and kept it over there. So with iterative runs I don't need to. So if you are not doing a refresh clone, or not just deleting the older archive wherever it's put down and putting down the newer one, then you know that pretty much everything is over there. So your data sets are also preserved. And at this point of time, one suggestion which I would give is that you can keep on downloading newer assignments as they keep on coming on the JIT link over here, but then please don't delete the older folders over there in which your earlier data sets were kept. Otherwise, every time you do a run and if your dataset folder is completely deleted, then you would see this whole messing up. So one simple thing is that always JIT clone onto the same location, so you know that it's always refreshed by the newer version of files which have come down from the JIT repository. And if you have made some modifications and kept it, then please make a copy on your separate JIT account and upload and keep it for your own purposes, and don't disturb the main repository which is downloaded and kept on. So here we start with the same way of you having 4 workers in parallel loading down in batch sizes of 1000 samples. So that goes out, and then I have my GPU availability check over here, which checks out man my GPU is available. So I can actually use my best way of accelerating out my codes. Now we start with defining what comes down as a sparse autoencoder. Okay. So now you see 2 different parts over there. One is that I initially start by defining a newer kind of a class, and this class of this particular class which I define over here is what is called as a L1 penalty. Okay. Now it becomes a bit confusing at this point of time to a lot of people, but let's keep it simple and do it. Okay. Yeah. So here the whole point was that while I am actually doing this autoencoder, so where's the first time where you would be looking into your sparsity? So you had say some 784 neurons which were connected down to 400 neurons, and you just had these 400 neurons again mapping back to 784 neurons, and this was the simple autoencoder which you are creating. Okay. Now I would like to add down sparsity at the end of this first layer, or which will look into the sparsity of the weights in my connections from the first hidden layer to my output which is being created over there. Okay, great. And the whole objective is that these layers will be, my connections from my hidden layer to my output layer will be sparse only if there is a over complete representation present in my earlier layer, which is from my input to my hidden layer. This has to be there, otherwise we cannot ensure sparsity in any way, and it goes around the way. In order to ensure sparsity, you will have an over complete representation, and you will, whenever you have an over complete representation, you will have a sparsity. So this has to go hand in hand within the learning paradigm over there. Now comes the two different aspects of it. So one is that I would need to define what is on my forward pass. Okay, so in my forward pass, what I am trying to get down is basically I find out that the total number of weights which have a value of closer to 0. This is what I just find it out. Whereas when I do my reverse pass or my back propagation, then I don't want any of these to have any impact and changes, while I need to keep one thing in mind, that these sparse autoencoders, they would ensure that you keep on like wherever it becomes a 0, then that 0 is stored over there, and then you, while in back propagation you also have the same thing been done. So here what I would do is that in my back propagation I need to have some sort of a memory to remember down my exact number of elements within the weights which were 0, and that comes down from this cloning based on a sign operator. Okay, so whether it was a 0 valued thing or something closer to a 0 valued thing, or whether it was a non-zero valued thing. So these are two things which I have to explicitly define into something called as an L1 penalty function. Now once that is defined, so first I will have to execute this particular part of my L1 penalty function over there. That is executed, then I come down to my autoencoder definition. Okay. So my autoencoder was that I had 784 neurons connected down to 400 neurons and 400 neurons to 784 neurons on my decoder side. Now comes my forward pass of the autoencoder. So what I do is I have my first forward pass, which is from my 784 neurons, whatever is my input, they go down to 400 neurons. Now at 400 neurons I will be putting out my sparsity for the first time. So and I want to have a sparsity imposition of 0.1, or 10% of my weights are supposed to be 0. That is by definition what I am saying down over here. Now this L1 penalty is basically a function which has been defined in this earlier case over here, and I have defined both my forward and my backward definitions for this particular new layer which we are proposing for the first time. So you can actually use this as a standard definition for proposing any newer kind of a layer architecture as well. So maybe you come up with your own neural layer architectures at any point of time, and you can actually use a separate function for defining that. We do the same thing in order to do this L1 penalty loss over here, and then whatever is the output which comes down over here, which is now sparse in some sense, and you have a decoder through which it goes down. Okay. Next I can just print my autoencoder, and then if I have a GPU available, I would just be using a GPU to do it. Now from there what I do is I use two temporary variables, and these are basically to copy down my weights. The whole rationale for copying down these two weights are like, before I start my whole training process, I would actually like to see like how they are initialized and how they look like, and what happened after my training with this kind of a sparsity coming down. So let us run this part, and so you print down your network architecture. Now if you look into your network architecture, at no point of time this L1 penalty loss is coming down over here, because this is just a function which has been defined for the forward pass. So you do not have a modification over the architecture, but you are just modifying the way your data would be passing in the forward pass of your network. Okay. Now my next part is to go on and train this autoencoder. Now based on our experience, we did see that over 20 iterations it does run out. Now again, from our prior experiences with the earlier examples which we are doing, it does take a significant amount of time to finish it out. So a few seconds. So I will just set this running while I actually start explaining you what goes down over here. Okay. So we decided to go with 20 epochs of learning and a learning rate of 0.98, and since I am training just a simple autoencoder architecture over here, which is just trying to find out the reconstruction loss and trying to minimize it. So my criterion or my loss function over here becomes MSE loss function. Okay. Now what I do over here is that I would like to have like these data points over there also stored for my like a later on point of viewing over there. Now what I start from that is I will start my training. My training will just be something a loop which keeps on rotating over the iterating over the number of epochs, and that's my epoch counter which is running down. Okay. So now as in with the earlier case, if we have a GPU, then we convert it onto a GPU variable, a CUDA variable which sends it over to the GPU, otherwise you just still have it residing on the CPU. Then you do a 0 of all the residual gradients present down over there, and then comes down the first part, which is a forward pass. Okay. So this is one forward pass of the whole batch in one single epoch. After that, what I do is I find out what is the loss function, so using my criterion, which is a MSE loss function, and this is just the difference between the input and output, because I was just trying to reconstruct whatever was given as input over there. Okay. Now I need to do a backward or the derivative of my loss, a nabla of my loss function, nabla of j, and here I get my derivative of the loss coming down, and then is my vanilla gradient descent or the simple strain plain method of gradient descent which I am using. If you remember from my last lecture where I was explaining you the theory of sparse autoencoders, you do not have any specific kind of a change coming down in terms of your learning rule. So the only thing is that we add a certain term onto the cost function, and how it gets added is because you have this forward pass and the backward pass, both of them defined, and in the backward pass is where I am adding this extra part on the gradient over there, and nothing more. So what this introduces necessarily is that my gradient is what comes down from the backward operator over the criterion function and backward operator over the network. Now that I have my gradient of my input available, I would just be adding this extra gradient, which is the loss computed in case of when I have my sparsity incorporated over there. So that's just the addition of the loss which I do over there, and that's what includes my equations whatever we had done over there. Now from there what I do over here is that this is just a simple trick to display down your outputs after a certain given point of time, and nothing beyond it. So let's just see how it has gone down. So yeah, it was good that you did finish training the whole thing, and over with 20 epochs we have somewhere achieved a loss of 0.058. Now if you remember in your earlier MNIST case with 10 epochs you were coming down to somewhere around 0.61 if I clearly remember, whereas here with using a sparsity we have not been able to come down to that level, but after 20 epochs we did go down, and clearly from the earlier example where you had two different data sets which are of the same empirical size in terms of the number of pixels and almost in the same dynamic range of gray values, you also did recall that it's not necessarily that you would come down to the same error limits for both of them. So here also it's something of the same sort. Now here what I try to do is basically in order to look down into what is the performance of my autoencoder over here, I would just like to check it out. So let's look into the performance of the autoencoder. So initially when it was trained down like at the start of the training, which is the 0th epoch, so you have all weights which are randomized and taken down from some sort of a Gaussian distribution and plotted down over there. So with that, if this is my input, then this is something which comes down as my output over there, and then you cannot necessarily make out anything out of it. Whereas after training, this is something which I get, it comes down as if a consolidated blob, not necessarily so noisy, it's a blob which comes out. It looks like a mixture of maybe 7, 3, 9, 8, a lot of things, and some decent probability around being a 7. So provided that you are training it for really longer period of time, or you are using some different kind of a training method. Instead of the gradient descent, you use some of the other optimization techniques, which at a later on point of time when we would be using, we study about them, you will be knowing that using some other techniques it might come down to a better point. But as of now, let's freeze at this point. So this comes down one where you have achieved some sort of fidelity in the whole reconstruction. Now I would like to look into my visualization of these weights. Now you remember that what we had done earlier somewhere over here is we had actually copied down all the weights while the network was defined, and these are all the random initializations which my network gets randomly initialized. Okay. So I actually bring those weights over here. Okay. So one is I can have my train weights, which I can extract actually after the training over there, and then I have my initialization weights, which were before the whole process was started. That is what is given down over there. Now when I write down this capital E, that's actually the weights of the encoder. When I write down those as D, then that's the weights of the decoder which comes down. So here let's look into these initial weights. So now this is what it was like at the start of the whole problem, and you remember that you had 28 cross 28 which were connected down to 400 neurons over there. So technically that means that I have 28 cross 28 or 784 weights which connect down to one single neuron, and this is that 28 cross 28 weight matrix which you see. And typically like if you look across these spacings, so you have such 20 cross 20 tiles. So you can just count it: 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 such ones, and on this side also you have 20 over there. So in total there should be 400 such small tiles present over there. Now once the whole training process is over, after 20 iterations over there, this is what these weights start looking like. And one thing what you can see is that they have changed, not necessarily that they have come down to a convergent point or something, but there has been subtle changes coming down, and some of them look like as if they are taking structures like 0, 1, 7 something over here, something rough. So provided you train them over a really long period of time, maybe set it down for 200 epochs and go and have your cup of coffee, tea, or finish off your dinner, lunch, whatever you are doing, and then come back in 30 minutes or so. In most of your systems it would be trained down for 200 epochs by then. So deep learning doesn't take that much of time, as a lot of people are scared about it. So then you would be able to actually see down the changes which come down. The next part what we look into is what is the actual way of weight updates which have happened. Now this is a very crucial point, because what we have done over here is just subtracted the original random weights from the current version of the weights after training, and these indicates those particular locations where there has been changes. Now if you look into these changes over here, these changes are something where you would be able to see down numbers. Now typically most of the updates have been in the center region, and that's quite obvious because whatever images of these numbers, handwritten digits you had, they had most of these actual line patterns which were at the center point. They were not located at corner places or anywhere, and that was the reason why you did not have any updates coming down in the corner, but most of the updates were from the center region. Also you see that they are somehow congruent to the numbers where it was trying to come down, and this is the first belief that if you are training it down over a longer period of time, so this would keep on converging over and over again. This would be the sort of a guidance principle of how the weights are getting updated, and eventually the final thing would start looking something like this, where each of these weights are tuned down to a particular number. So this is what I leave on to you guys to do out of your own interest. So this is about how all of these things are connected from my encoder to decoder. This is one part of it. The next part is to look into the weight visualization for my decoder, and that's where this capital D comes down. So all my weights from the decoder. So initially I had already stored down my weights from the decoder, so that was something. If we go up over here, when I had defined it, so I have my weights of the decoder as well, which I had stored it down, and then after my whole training is over, I again pull out those decoder weights from my network. Okay, now my whole objective is to repeat the same thing and then start looking into the decoder weights as well. Now this is something which is present at the initial part of it, and clearly if you look into these patches, so I have 784 neurons which were connected to 400 neurons in my encoder. Now I have 400 neurons in my encoder as output of my encoder, which are connected down to 784 neurons on my decoder. Okay. So now what I would have is that there is a small matrix of 20 cross 20 or 400 weights. So that's this small matrix over here, and then since I am connecting it to 784, so there should be 784 such small patches or matrices of weights. So it's a 28 cross 28 array which should be there. Let's just count it: 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. and count down on the vertical direction, you would see such 28 tiles again. Okay. Now over here is where I see my weights which are after my training. Now it doesn't look much of a difference. Technically saying, like most of you would say, it's as noisy as it was in the earlier case as well. Yes, it's noisy, but then the intensity of the noise has somewhat decreased. One thing you need to keep in mind is, you remember that these gray values, what we had seen in the earlier cases also I was explaining, that they are what are 0 values, and all the blacks are negative values, all the whites are positive values which are over there, and this is normalized into its dynamic range, and that's why we don't have that. This is just for visualization purpose. You cannot technically infer out on the values just looking over here. And then if you look into these weight updates over there, you don't necessarily tend to see any patterns. There are some wavy things and some really discrete way. However, there is one interesting point which you need to look into over here. Here when you see in this one, most of the values were either highly negative and highly positive. Here a majority of these values tend to become down as zeros. And that's the point of this L1 sparsity which comes down, because now that you have all of these gray values which you see, they are 0 valued numbers which comes down, and this is something which gets imposed from here while you had just high positive and high negative values to here when majority of the values are actually 0 valued on the weight matrix over there. So this whole thing comes down because you have an L1 penalty you had imposed over there, and that was possible because a lot of these weights you see over here, they look similar to each other. Say this weight looks pretty similar to this weight, looks pretty similar to this weight, or looks pretty similar to this weight, looks pretty similar to these weights. Now the moment is you will be able to get down, whereas this weight looks very dissimilar. Okay, so you will have very less number of such unique weights which are available, and then since whatever you are doing over here is just a combination, a weighted summation of the outputs coming down from one of these layers. Now most of these neurons, they would actually have a similar kind of an output which comes down, and you can pretty much do away with most of the neurons and keep just 1 or 2 neurons over there and still get an output coming down. And that was the reason, the whole rationale why over here you see a lot of these weights actually go down to a 0 value, and that's really helpful in case of dealing with sparsity. Now you would see that the weight updates which happen over here, they are also quite near to 0 value, but there are certain high and low changes coming down because you had to bring down those high positive and high negative values on to quite closer down to actual 0 values coming out. So that was all about these visualizations. And finally what we do over here is the simple old trick, which was I have trained down my whole encoder with L1 sparsity over there, and now I would like to modify this autoencoder in order to form a classifier. So what I need to do is I necessarily need to remove out my last decoder layer and then add my classifier module which connects down 400 neurons to 10 neurons, and then I can start my classification trainer. And this classification trainer over here trains over the standard 10 iterations using negative log likelihood loss function as we had done in the earlier case. So let's just set this running over here. Okay. Now as I see over here, you would see that it starts with a starting accuracy of 78%. Now this is if you remember it from the earlier one, this is really high, because earlier case we started somewhere around 66% on the starting accuracy, whereas here we have started down with a starting accuracy itself of 78%. Now one question you might ask is why is it so? Why did we start with a higher accuracy? Now, one thing you need to keep in mind is that these kind of networks, the moment we started introducing this sparsity, there was one thing. In order for the network to be sparse, you need the earlier part before sparsity to be over complete, otherwise the network cannot be sparse. Now the moment you are having an over complete representation in the earlier case, you see that you tend to have similar representations grouped down. So you are now coming down to dominant group of representations, and that means that the noisy representations are getting ruled out in the whole process. So as we keep on getting noisy representations ruled out, which means that features which are really irrelevant to this particular problem of classification, they don't come into play. So and for that reason we start with a very higher accuracy. However, the final accuracy is almost of the same lot. It doesn't change, because in the earlier case you had about 92%, we trained it over and over for 20 epochs, so you went down to 92%, and then here you might not necessarily get down, but your starting estimate in this case is a much better estimate than you have in the earlier case without having the sparsity. So, if you look into each of these classes and how much they come down, you still see that for class 5 in the earlier case it was about 55%, 85% accurate, and here we are barely 84.7, which is almost the same amount of accuracy. There has not been much of a change. However, the features which it has been learning over here are something which are more congruent to be representative of the numbers which are handwritten. So, with this we come to an end of lecture 19 on our whole aspect of trying to train down an actual autoencoder with sparsity included over there, and with this concept we have shown you for the first time about how to actually start defining your own kind of layers as well, including if you want to just have some customized cost functions coming down. So, in the next lecture we would be covering down on top of this one, which is to come down with the next aspect of a denoising autoencoder, and then how does a denoising autoencoder help you to learn better weights as well as really clean down the noise from any of these results. So, for then stay tuned and thanks.